when we look at curve sketching, right, we've looked at sketching pretty familiar types of curves. We've looked at sketching like y equals to x squared, y equals to x cubed. I mean, what other kind of curves have we looked at in this course? Give me another one.
Y equals 3x.
What is that? 1 on x?
1 on x, we're going to go with
Y equals 3x is your exponential, right? And you're expected... Well, we got more.
circles, x squared plus y squared.
Have we looked at circles?
Yeah, of course we have.
I can't remember.
They curve functions. They curve for everyone. You
Okay.
didn't say function, you said curves.
Okay, so this is true, this is true. So, with these types of curves, right, how do we sketch them? We essentially sketch them based off sight, right? We sign them based off sight. And we say, okay, I recognize what this is, I know what this is, I can draw it. Sometimes though, like, if I give you something like this, I can't look at that and just be like, I know exactly what it's going to look like, right? These ones here, yeah, we've drawn them so many times that you can draw them and you'll be like, hey, yeah, there's your parabola, there's your cubic. Ooh, no, that's not a cubic. There you go, right? But this one, I'm looking at this, I'm like, not too sure what that is. So, what I'm going to do is I'm going to give you a little menu. It's our curve sketching menu. It's basically going to tell you how to sketch any type of curve that you get. And it's using calculus. So it's going to rely on the fact that we can find stationary points. We can find points of inflection. That's going to help us work out what this is going to look like. What we want to do with this menu is, for any type of function, we want to go through, tick these off along as we go, and that's going to give us a better picture of what this function is going to look like. So just looking at this, without actually doing any calculations, thanks. Without actually doing, I'm not going to lose this one this time. Without doing any calculations, just have a think about what this is doing. You're finding a kind of big picture of this, and then you're kind of zooming in to the specific parts, right? We start off with the domain, and we're like, hey, are there any domain restrictions here? How much is the domain going to cost? It's about one whole function.
One function?
Yeah, one function.
It's expensive.
Pretty pricey, pretty exy. So we're looking at a domain here. Is there any restrictions? Generally, we only have restrictions when we look at things like fractions or square roots. Right? These kind of things can affect the domain, generally. We don't really have anything like this here, so that's not really going to be an issue, okay? The other thing is you want to think about what type of function this is, right? And that can be thinking about things like, hey, we've learned about types of functions back in year 11, so that stuff's pretty useful. We looked at like odd and even functions. We looked at, also, just think about, hey, what about powers? Like what kind of function is this? If we've got power of 3, we're working with a cubic, right? So like, you know, cubics, etc. All of that can help you. All of that can help you think about what this is going to look like. We don't know exactly where the points are or, you know, what even like the stationary points are going to look like. We don't really need to. We just want to think about, hey, a big picture look of this. So first of all, for this one, I know there's no domain restrictions, no fractions or square roots or anything. And I know that this is a cubic. So I've got a kind of rough picture of what that's going to look like. Intercepts. When I'm looking at this, Joel, intercepts, what are we thinking about for intercepts? What do we usually do for that? How do we find intercepts? Yeah. We let x and y be 0. Right? So that's same as always. So we let x equals 0 for y ints. We let y equals 0 for x intercepts. So let's go ahead and do that now, step 3, right? So we've got here now y equals to 9x minus x cubed. So for, let's go x equals to 0. Oh, this is really nice. We just get y is equal to 9. Ah, that's nice. 9 times 0 minus 0 cubed. This is why I write working out, because I say things and I write something else. Equals to 0. So the y int at 0, 0. I mean, if there's a y int at 0, 0, then there must be a x intercept too, right? Because that's the origin, yeah? So that's passing through both of these axes. Or maybe there is more than one. Let's find out. So for x intercepts, we let y equal to 0. I don't know why I wrote 4x equals to 0. We should write...
We know at least one of the intercepts is going to be at.
Exactly right. Because it's at 0, 0, we know at least one of them is going to be there. And in fact, what I might do is I'm going to start drawing this up here. Yeah. And we've encountered this problem before, right? Like, again, I don't know like a cubic formula. There is a cubic formula. I looked this one up this time to solve cubics. But anytime I say something like this, I suggested that we look for things that are in common, right? And what do you have in common here? We've got that factor of x that's in common, so we can factorize that out. Okay, so we've got two things going on here now. You've got either x is equal to 0, or 9 minus x squared is equal to 0. So x squared equals to 9. What are my solutions for x?
So which one is the
Plus or minus 3. Positive or negative 3, right? So, like we expected, there's a solution at that x equals 0 because we already found that one, yeah? So I know now, actually, what are the x-intercepts or y-intercepts? I've got one here. I've got one at minus 3, and I've got one at 3. And with cubics, right, I know generally what the shape is going to be like. It's going to be something like this, or maybe something going the other way. I'm not too sure. But I'm starting to put a picture of all this information and starting to put this onto a graph of what this is going to be. All right, what's the next bit? Except for asymptotes, right? Well, asymptotes really only occur when you have fractions and things like that. So in this case, it's not really applicable. But this is just like a general guide for you of how to do these, because you will get functions where you may need to actually sketch things involving asymptotes and things like that. That was like the hyperbola that we looked at before. All right, and here's where the calculus gets going. Right, stationary points and points of inflection. Like the past couple of lessons, we've been looking at building our skills and finding them, classifying them, drawing up tables and all this kind of stuff. And it's leading up to this point here, right? Because we're doing all this work and we're not really doing much with it. We actually want to sketch them now. We actually want to draw these onto a graph. So stationary points. Angus, can you walk me through how we can find stationary points for this function? Does anyone also need the x and stuff? Yeah, I'll leave it there.
Find any turning points.
Yeah.
Find any points of inflection.
Yeah.
Sketch for y equals beta.
So how do we find,
It says in the book.
okay, how do we find turning points? What is a stationary point?
Yeah, when the gradient is 0, so you have to take the derivative.
Yeah, so we let y dash equal to 0. This is for stationary points. And always just like write what you're doing, because often like a marker's going to look at a page and see like there's all this math here. Like actually communicate what you're doing, right? So we've got 0, well actually we need a derivative first, right? So y dash would be equal to 9 minus 3x squared. So we're going to get 0 is equal to 9 minus 3x squared. And then we're just going to solve this to find the stationary points. So we're going to get 3x squared is equal to 9. X squared is equal to 3. And the numbers won't always be nice ones, right? Joel, you still need this one?
Yeah, no.
Okay, cool. The numbers won't always be nice. What do we got going on here? We've got x is equal to plus or minus the square root of 3. Okay, so that's what we're working with. Not particularly nice numbers, but something to keep in mind. Now, last lesson, I said that there's two ways that you can classify them, because we know that this stationary point, it could be a minimum or a maximum or a point of horizontal point of inflection potentially, right? But there's a few ways to classify them. We can use the table method. Did we like using that table method? It took a bit of a while to do, right? Because you have to substitute all the values around it. So you can do that. But then I also introduced another method, and that's called the second derivative method, just to jog your memory, right? If you have a curve like this, there's your maximum. That's when f dash of x is equal to 0. But we also notice that it's concave down. So that's when the second derivative is less than 0. It's concave down. What was the other alternative, Joel? What else could we have? We could have this guy.
F double dash of x is greater than 0.
Yeah, concave up. So that's the other condition that you can look for, yeah? That's for the minimum, that's for the maximum. So the idea is, okay, if you don't want to do that table method, you don't have to. This way can work, right? I actually ran into some problems using it last lesson, but I'll talk a bit about that in the next example. But if we want to find points of inflection anyway, this can be a good solution. So why don't we try this? So we'll find y double dash. So we just derive this guy. Luan, do you want to derive this one for me?
6x.
Yeah? Be careful when you signs there.
Oh, minus.
Yeah, cool. Right, so we take that, we get the second derivative. What's this used for now? Well, we want to now test what's the concavity at these points. Because if I can test the concavity at these points, and I can see whether it's, if it's either positive or negative, then I can determine what kind of stationary point it's going to be, right? So we'll say at x equals to root 3, positive root 3, what's y double dash equal to? It's a negative number, right? You can calculate that. I think it's like roughly, I think it's like 10 point something.
Negative 6 root 3.
Yeah, negative 6 root 3. That's obviously less than 0. Yeah. So therefore, right, if the concavity is less than 0, it's concave down. So what kind of point do we have? We have a, yeah, there's a max. There's a maximum at root 3. Now we need to find the other point. How do we find that other point? We have to substitute it back into the original, right? So there's a lot of interactions going on between like first derivatives, second derivatives, and the original function. You just have to be pretty confident with what each of these represent. The original graph gives you the points. The first derivative gives you gradients. The second derivative gives you concavity. So make sure you just make a note of that when you're doing that. Right, so points, derivatives, concavity. Can you substitute that into the original and just get a point? Can you also find and classify the next one for me? I'm going to go try that for me.
It's a nice way of writing.
It is actually quite nice. And as a value, just because like, you know, when I want to plot this,
It's not 3 root 3.
it can be written as 3 root 3, yeah. That's fine, I'll leave it like that for now. I think this is like 1.7 something, and this is like 10 point something. Is it 10 point something, Joel?
10.39.
Yeah. So the reason why I would also write the decimal values is because when you're sketching this, right? Like, although it's nicer to leave it as exact, if you think about sketching, you actually want to know where these are. You want to know where these turning points are. So I don't know what, no. Put in your calculator, yeah. But just so we can start to formulate what this is going to look like, you can go to root 3 and go up to here. It's roughly going to be around here. You're looking for a maximum around here, roughly. So, you like that spot? Yeah, okay. All right, what about our next one? So we want to test at x equals to minus root 3, right? Harry, do you want to do that one for me? I know, that's why I picked you. Seemed like you were trying to avoid me.
No, I wasn't. Can you offer a cupcake for me?
The sacrificial cupcake.
I gave you a sticker.
So we want to put this into our second derivative now to test for concavity, but we know that because we've got minus 6 times negative root 3, again, it's going to be like pretty similar. It's going to be the same value, but just now a positive 10 point something roughly again. That's greater than 0. So what does that mean then? Concave up. So we've got this situation going on here. We've got a minimum at what? Well, we can just put it back into the original, right, for the points. So we get negative 9 root 3. Here. Oh, yeah, sorry, yeah, cool, thanks. Thanks, Laura. And then negative 9 root 3 minus root 3 all cubes. Yep. Yeah, awesome. And I think it's like the same value, actually, but just down over here, right? So here's our minimum. Can you start to see how this is coming together, right? We've got this idea of a picture of a curve that has to pass through these 3 points. We've got a maximum going on here. We've got a minimum going on here. I'm starting to formulate what's going on. One last step that I have to do though, and what's that last step? Sorry? It is a long process, but this is probably the only question that I can tell you that you'll probably be guaranteed to get. And I say probably like 3 times because I can't guarantee anything, right? But if there's a question that I would put money on that you'd get in an exam, an HSC exam, it'd be one of these, yeah.
How much is the mark for like a question like this?
Good question. So they probably wouldn't just ask you to sketch, because the question I'm asking you to do is like basically sketch y equals to, what was it? 9x minus x cubed. They would. So they would first say, okay, can you first find any stationary points that may be worth like 2 marks? Find any inflection points that could be worth 2 marks. And then sketching, well, that probably has to be worth 2 marks as well. Like this could be potentially 6 marks in your HSC exam. That's like 6% of your exam, right? If you're gonna lose 6 marks, this is not the 6 marks you wanna lose, because this is 3 marks for you if you can just practice this enough times with this process. Points of inflection. We take our second derivative and we let y double dash equal to 0, right? So we're gonna get 0 is equal to minus 6x, x is equal to 0. So there's a possible point of inflection here. We can't know for sure until we do something. What do we have to do? Think back to last lesson.
So we have to check now.
Yeah, we have to test. If you do not test, right, you're really not doing this question properly. You have to test for this one, right? Blake, what did I say? What values did I say we could test usually? If I look at second derivatives, right, I want to test 0. I know it's going to be 0 there, Blake. Yeah. But what values do I usually test on either side? Yeah, you just test 1 on either side. Easy. And in fact, it's quite nice here, right? Because you can very clearly see this is going to be positive 6 when you put it in. This is going to be negative 6. So we've got a change in concavity. Okay. So you can think about, I draw this diagram. They draw it like this, like concave up, 0, concave down, right? You can sort of tell, you reckon? Yeah. So there's a point of inflection. There's a point of inflection at 0, and we already know where 0 is when x equals to 0. That's one of our intercepts, right? 0, 0. So not only now is this an intercept, but it's also a point of inflection. Now you may be thinking to yourself, hey, I could have told you that, right? Like that's probably what it would have looked like anyway, okay? But the reality is the question, like I said, they'll break it down into these 3 steps. Find stationary points, find inflection points, and then graph. So let's try and connect this up and do this as neatly as possible.
That's pretty neat. I think it's a bit like
How do we go?
at IRL, it's kind of like squishy. It's squishy.
Bit more squish, you reckon?
I didn't mind like that.
Yeah, that's probably better. Now here's a sketching tip for you. If you draw this and it doesn't quite work out, rather than trying to redraw the same thing, I'm going to cheat. I'm just going to move my x-intercept slightly, my x value slightly, so I get something that's a bit more accurate. So these should be minimums. And where do these occur? They occur at these points here. So what was it? 9. Yeah, let's leave it as exact, because I guess that's probably better, hey? And then 9 root 3 minus root 3 all cubed. Yeah. And there's your point of inflection, and there's your graph, right? It's a long process, yeah? But it's a question that is quite common and is a good part of your kit when you're trying to approach exams like this. Let me give you another one.